Are you ready to stop writing jargons in TensorFlow, keras, or pytorch? If so, let's go. Today we'll be going from understanding how a single neuron works to understanding how a layer of neurons work. Alone, we can do so little. Together, we can do so much. Helen Keller. Let's see how we can help our neural network do much. At the core of a neural network are neurons, which may make the behavior of biological neurons in our brains. Imagine you're trying to predict the weather, whether it be snowy, sunny, or rainy. Each neuron in the input layer could track specific features like temperature, humidity, and cloud coverage. These inputs are then transformed using weights and biases, and they are sent to the next layer, which is typically the hidden layer. Each neuron in the hidden layer receives inputs from all neurons in the previous layer. To calculate the outputs of the hidden layer neurons, we assign weights to the connections between the input layer and the hidden layer. Each neuron has its own set of weights, representing the strength of its connections to each input, which would be those features we talked about. Additionally, there's a bias term for each neuron, which allows for fine-tuning. Now let's dive into some code to see how the process works in practice. We'll use Python to create a basic neural network with a single hidden layer containing multiple neurons, but we'll start from a single neuron. First comes the input, which is just your data. Then each neuron has a set of weights that measure the strength of its connection to the input. It also has an internal bias, which measures how much the predictions deviate from the true value. To get the final output, we add the products of the inputs and their corresponding weights, and then we add the bias. In this example, we have an input layer with 3 neurons and the hidden layer with 4 neurons. We calculate the outputs of the hidden layer neurons by multiplying the input values with the corresponding weights. Then we add the biases. Later we'll talk about activation functions and how to apply them. You can see that the output is no longer a single number, but now a list of numbers, or we could say a list of outputs. By using this multi-layered structure, neural networks can capture the complex relationships in any data. The weights and biases are adjusted during the training process to optimize the network's performance. The struggle lies in finding the best combination of weights and biases that minimizes the network's error or maximizes its accuracy. This optimization process is often done through techniques like gradient descent, which allow the neural networks to learn and make accurate predictions. That's it for today's video. This video is the second in this series. If you want to understand other things like backward propagation, parameter tuning, optimization, loss and activation functions, subscribe and hit the notification bell so that you know when I drop next week's video. For now, you can click any of the 2 videos on the screen to learn how to program a quantum computer or to watch the previous episode if you have not. Bye.